The gas law I will be explaining today is Boyle's gas law, the law that explains how, if all other variables remain constant, as the pressure of a gas decreases, the volume increases, and vice versa. Boyle's gas law was discovered in 1662 by the physicist Robert Boyle. While experimenting on air with his fellow physicist Robert Hooke, Boyle discovered that when pressure and volume are multiplied together, it creates a constant. Pressure is the force that a gas exerts on the walls of its container. The volume of a gas is the same as the volume inside the container the gas is inside of, as long as the molecules fit into the container, which is a measure of how many molecules can fit into a container. Volume and pressure have an inverse relationship because as volume is decreased, which means there's less space in the gas's container, there's less space for the molecules to spread out, which means that the molecules will be hitting the edges of containers with more force, which is an increase in pressure. The other variables in the ideal gas law, moles and temperature, do not partake in Boyle's gas law. In Boyle's law, it must be demonstrated in a sealed container to keep the mole amount of molecules at a constant, and the temperature, the measure of kinetic energy of molecules, must also be kept at a constant. This explains the variables in Boyle's gas law, which is that the pressure of a gas multiplied by the volume of gas equals the pressure of that gas multiplied by the volume of that gas after either pressure or volume is changed. For example, I will perform a calculation to show Boyle's gas law. Nitrous oxide is an anesthetic. The pressure on 2.5 liters of nitrous oxide changes from 105 kilopascals to 40.5 kilopascals. If the temperature does not change, what will the new volume be? First, we will set up the equation. The pressure of nitrous oxide, 105 kilopascals, multiplied by the volume of nitrous oxide, 2.5 liters, is equal to the volume of nitrous oxide multiplied by the pressure of nitrous oxide after a variable, pressure, is changed. Pressure is changed from 105 kilopascals to 40.5 kilopascals. First, we multiply the original pressure and the volume together, which equals 262.5. Then we will divide both sides by 40.5. This makes it so the new volume of the nitrous oxide sample is equal to the quotient of 262.5 and 40.5, which is 6.428 liters. This is Boyle's gas law. Here, I will be performing a demonstration of Boyle's law. I take this slightly blown up water balloon and I put it in a syringe. I close the syringe and I place my finger tightly on the other end of the syringe to create a vacuum so no air is released, which keeps the mole amount stable. As I increase the pressure put on the balloon, the volume decreases. And when I release my finger, the volume and pressure return to normal. As I put my finger back on the end and decrease the pressure put on the balloon, the volume increases and I take my finger off in the end, and again the volume and pressure both normalize. There are two properties of gas other than their pressure and volume that are very important in this demonstration's success. The first is that gas fills up whatever container it is in, which is why the syringe seems full when I put my finger on the end. The second is that gas is mostly empty space, which is why I could push the plunger of the syringe down when my finger was on the end, closing the syringe. Here's the syringe before I started moving the plunger. I put my finger on the end of the syringe to ensure the mass of the air molecules remain the same. When the plunger is moved down, the pressure on the air molecules is increased, which forces the air molecules closer and closer together, which decreases the amount of space that the air molecules take up, and the balloon's size decreases. When I removed my finger from the end of the syringe, the added pressure is released and the balloon grows back to its normal size. When I placed my finger back onto the syringe and moved the plunger upwards, the pressure on the air molecules in the syringe is decreased by increasing the volume of space that the air molecules take up. The increase in volume and decrease in pressure pull the air molecules apart from each other, and the balloon size increases. Removing my finger, again, returns the pressure to its normal state, also returning the volume of our balloon to its normal state. One real-world example of Boyle's gas law has to do with the bends. The bends is when nitrogen bubbles from the seawater get into a scuba diver's joints at high pressure, and then the nitrogen bubbles expand, causing extreme pain. Now for the explanation. As the scuba diver dives deeper into the water, the pressure increases and the water becomes much heavier on the diver. When the pressure increases, the volume of the nitrogen bubbles in the water decrease, allowing the nitrogen bubbles to get into the joints and bloodstream of the diver. If the diver ascends quickly, the nitrogen bubbles in his joints will rapidly expand, causing extreme pain in the diver's joints and bloodstream. In some sudden depressurizations, the nitrogen bubbles in the diver's joints and bloodstream can expand so quickly that the diver can even instantly die. This is a prime example of Boyle's gas law because it shows the inversely proportional relationship of pressure and volume.